x minus y theorem. And at the end of the day, this is just the long exact sequence attached to the pair x minus y. And then the substituted the isomorphism given by Leray-Thom-Gysin. Anyway, okay. So maybe I write it in a homology also. So in homology, you just change the direction. Maybe homology with Q coefficients or whatever, or Z coefficient doesn't really matters. Okay, so maybe so let's go this map. We will call it the residue map, and this map we have already discussed what it was. This sigma map. So in any case, let me explain what was this sigma map. We had this y, we had the ambient space x, we had this let's say delta in hm plus 1 minus c 1. And so to each point we represented by delta by, let's say, simplaces, and then we made thickening of delta in the sense that to each point of delta we added a circle. We replaced each point of delta with a circle. No, actually not circle, but it has to do with the codimension. So this is a sphere of dimension c. Because y, remember that y in x has codimension c. And no, but just a moment. C when it is 2. Just a moment. M plus 1 minus 1. Let's just. So it is m plus 1 plus c. Yeah. Let me see. Let me. Yeah, I think. The c. So here from dimension m plus 1 minus c, we have to jump to dimension m. So maybe just very fast I check this one, sigma. Yeah. Yeah, okay. Anyway, then this sigma, this delta going to sigma delta is constructed in this way. So by definition, residue map is dual to this sigma, which we constructed topologically. Today, we will need to construct the residue map algebraically, but from the topological point of view. So what defines the residue map? So I want to define residue map saying that this is dual to this one. So in any way, I have to define its residue of, let's say, omega. So omega. So omega being here, I have to define what is this. In order to define the residue omega, I have to say that what is its integration over delta. So this is then I will have a residue of omega here. So if I take delta here, this delta here, I have to say what's the integration of this one here. And by duality, this means that this must be the integration of omega over sigma delta. So this identity will define the residue map uniquely, but of course it doesn't. It's just a definition. So what we are going to need is that the Rham cohomology, it is possible to construct in a purely algebraic context. So we will need the concept of the residue map in a purely algebraic algebraic way. So okay. Let me see what I want to say else. Okay, so I will apply this this situation to the pair. So then, in order to announce the Griffiths theorem, x for me will be Pn plus 1. I will take x as Pn plus 1. This one I mentioned in the previous lecture. And the y will be, I will denote it by x smooth hypersurface, x smooth hypersurface in Pn plus 1. So today I will a little bit repeat what we were I did in the previous lecture. So maybe again write down the long exact sequence. Hn plus 1, the Rham Pn plus 1 minus x Hn x. And actually I am writing from, let me see, I am writing here, here, and then here. So I have reversed the direction. Hn plus 2, the Rham Pn plus 1. And then here it comes Hn plus 1, the Rham Pn plus 1. So this is the residue map that I needed to a little bit describe. Okay, so let me see. So maybe first, so in the last lecture, during the proof of Noether-Lefschetz theorem, I was saying that at the end, in order to capture the cohomology of this guy, we need just to understand the cohomology of this hypersurface. Maybe if whatever I am telling it is valid for arbitrary n, but maybe, for example, for let us focus n even, because at the end we will be interested in the Hodge conjecture for hypersurfaces, which is completely open. So when n is even, this cohomology is 0, and this we know that this cohomology is one-dimensional, and actually this guy is generated by what? So let's work our complex number. This is generated by theta n half plus 1. Remember that the theta was the generator of the cohomologies of the projective space. And okay, so let's a little bit focus on this one. So at the end of the day, you see that this is maybe something also I have to mention. This is before proceeding. So we had this theta n half also here. So the same theta, you restrict our x, and then I didn't produce any new notation. I again denoted by theta. And then when you make it power n half, then you will get elements here. And maybe it's a kind of exercise, especially for Felipe, who did the algebraic topology last semester, that this theta n half is mapped to theta n half plus 1. And with some coefficient, and this coefficient is not 0. Anyway, what I'm saying that the end this element will be mapped to something to the generator of this guy. Okay, so let's prepare the ground for. Okay, so what we have here, so H and the Rham X primitive. Well, in my book I put 0 because of some old notation of Griffiths, but Griffiths himself and many people after him just they used this putting prim also primitive. So this primitive will be just a kernel of what this map, the kernel of this map. That's Hn plus 2, the Rham, Kn plus 1. And you see that if n is odd, I mean this notion of the primitive is the same as this primitive, and the whole cohomology are the same. But we will focus on the even case. Anyway, let me again. Let's just consider this one as Hn the Rham X. We will have a codimension 1 subspace of this one. This is of codimension 1. Codimension 1. And then we have this element, the polarization, theta and half. And at the end of the day, we have this Hn the Rham X is just the sum Hn the Rham X plus, no, not, but this isomorphism is, this is the sum C theta and half. Anyway, any element in cohomology is obtained by sum of some primitive plus this. And maybe one important observation, that theta and half is a Hodge class. So if you are interested in Hodge cycle and Hodge class, this is already a Hodge class. Let me again make a picture, remembering. So if this is X, this is Pn plus 1. If we make this Pn half plus 1 and intersected it with X, let's say a dimension of Pn half plus 1 intersected with X is n half. And this cycle it will give you an element in the homology, and these are Poincare dual. Theta and half is Poincare dual of this cycle. So anyway, this polarization is an algebraic cycle for free because of its definition, because polarization is just obtained by taking hyperplane sections of X. Okay, so anyway, so this means that if we are interested in Hodge cycles, Hodge classes here, basically we can work with this primitive cohomology. And And the Griffiths is so maybe so we take this one, this was equal to 0. So maybe the n even. Then we have h n theorem n plus 1 pn plus 1 minus x, then residue map. This will be isomorphism between this the primitive part of x, because here is 0, and then we have this along with that sequence. Yeah, okay. So, okay, maybe I have to say something about Hodge filtration. Anyway, remember that this guy has a Hodge filtration. F0, oops. This doesn't work also. F0, F1, Fn, Fn plus 1, which will be 0. And well, you can just define the Hodge filtration of the primitive part by just intersecting. So let me write it. Fi Hn the Rham x primitive by definition is just Fi Hn the Rham x intersected with the primitive cohomology. It's and the Rham x primitive. Okay. So anyway, we have this one. Okay, maybe I have to mention that. So this is also important to mention. So this guy, this theta n half is in, since it is a Hodge class, it is in n half. It is f n half theta, because theta is a Hodge class. And let me see what else. Okay, maybe this one I have to mention. So, or okay, let's go to the announcement of the Griffiths theorem. Maybe I will write first here again the isomorphism. Something that in the future we will do it. I defined it residue topologically, but it is possible to define this residue algebraically. So we will reach to this point. Anyway, here we have a Hodge filtration. Maybe right. Fn. But here also we have a, let's say, pole order filtration. Order filtration. What is this pole order filtration? Oh, just a moment. Oh, Felipe, você estava gravando ou não? Ah, então tá gravando? Eu vou prestar tua gravação. Minha gravação, não sei, falhou alguma coisa. Ah, tudo bem, tudo bem. Tá, então depois você compartilha comigo no Drive. Ok. Okay. So we have here polar filtration. The polar filtration here, so that again, remember that Pn plus 1, we have the hypersurface here. So differential forms here, they have polar along, they are algebraic differential form, and hence they have polar along x. So let's say polar 1, polar 2, polar k. So the Griffiths theorem, something that will say that at the end this filtration, by changing these numbers here, they are mapped to each other. It is okay. So let me again share the screen. Your entire screen. But once again. Okay. So in the book I have written, in my first book, I have written the term of Griffiths in a weighted projective space. In this case, it is actually, this generalization is due to Stimbring. And I will try to write it in the case of usual projective space. So let me write it once again in the here. Okay, so first of all, by Atiyah-Hodge theorem, minus x. It is this is given by actually this is Atiyah-Hodge, but anyway, Griffiths in this case also he proves explicitly. So it will be global. Maybe just let's write it in a so global differential forms in Pn plus 1 of n plus 1. So what is this notation? This means that we are n plus 1 form in Pn plus 1 with poles of arbitrary order. So star means arbitrary order along x. So this modulo the exact ones. The H0 Pn plus 1. So it will be omega n star x. So global, this is the global n form with poles along x of arbitrary order along x, and then their differential. So this is basically Atiyah-Hodge, but then it comes this the Griffiths part. So here we have let me say okay, so under this, let me say, let's say under this isomorphism, then we can talk about the Hodge filtration here. So we have this Fi here. So let's define Fi residue minus Fi of here. And again, I will use it the same notation Fi. So what is so we have a Hodge filtration here. So first of all, Griffiths theorem tells that Fi it corresponds to elements such that for some representative omega, pole order of omega along x is less than or equal. Let me make the proper translation. So it will be so for pole order equal to 1, it must be Fn. So it will be Fn plus 1 minus I. So in particular for Fn, the pole order must be less than or equal to 1. So in any case, the first part of the Griffiths' theorem says that how to capture this cohomology, and maybe it is important that I define the Hodge filtration purely an algebraic, but at the end, Griffiths was using the Hodge filtration, the original definition of the Hodge filtration, first using a PQ form, Hodge decomposition, and then defining the Hodge filtration. And maybe something else I also tell have to choose a basis. This is also very important because at the end I want to turn, let's say, a lot of arguments in Hodge theory to linear algebra. We must be able to choose a basis of objects, a basis of Hn plus theorem. Okay, so I have to choose a basis, and for this, let's assume that let's give let's write f. Here I will use capital X because small x I will use it for another purpose. So let's give Fn f homogeneous polynomial of degree d. And okay, so I will form this Jacobian ideal. Jacobian ideal of f. It is just a partial derivative xn plus 1. This is inside the ring of polynomials if we denote with Dixon. So so I will take this Jacobian ideal, and then what? Maybe one easy exercise in algebraic geometry. X is smooth. Actually, this is another way of defining the smoothness. Cx divided by Jacobian of F is a finite dimensional C vector space. So, well, in Hodge theory, they do not call in this way, but this is in the singularity theory. It is also called the Milnor vector space. Okay. Now I would define a basis of the de Rham cohomology of smooth hypersurfaces. So this will be so in our case we started from X, so X is smooth, so this will be finite dimensional. Since polynomials are generated by monomials, we can choose a basis of monomials, let's say X beta. This is the abbreviation for X0, beta 0, blah, 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 X n plus 1, beta n plus 1 for some set. So we can choose this one. So a basis. So I am writing the Griffiths, a basis of Hn plus 1 de Rham X Pn plus 1 minus X is given by this X beta in I. So I is my index set. So this omega that I wrote, and I will write it here also, this will be Fk. So let's say omega being this minus 1 to the I, xi, and then dx1, dx2, blah, 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 removing dxi, blah, 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 dxn plus 1, I equal to 0, n plus 1. And then the degree, so the degree of the denominator must be the same as the degree of the numerator, such that this guy goes to some differential form here, because it is written for the moment as a differential form in Cn plus 2. So in order to have the degree, so and then a k d was the degree of F must be degree of x beta plus, and the degree of this omega by definition, it is n plus 2. So Griffiths also tells us that the basis is given in this way. And what else? And then a basis of F. Oh, sorry. Now we have this F, capital F for the polynomial, and the F for the pieces of the Hodge filtration. So don't confuse, don't make mixture of these two. Okay. So the basis of Fi, it was pole order. Pole order n plus 1 minus. Let's say Fi, actually the quotient basis of this Fi is given by Estella with, so the pole order must be exactly, K must be exactly this n plus 1 minus A. And okay, so anyway, this is the kind of a full version of the Griffiths theorem for hypersurfaces that we are going to need. And I was planning to make a proof of this one, but at the end it is purely algebraic. So I have changed a little bit the plan. The plan is to try to apply to this theorem to the Fermat varieties, and first to a little bit play with the Hodge cycles and algebraic cycle with Fermat variety, and at the end, if we have time, we will return back to Griffiths theorem again. Okay, any questions so far? Okay. So, okay. Let me see what else I have to say. Anyway, the moral of the story with the hypersurface is that at the end, in order to capture the cohomology of hypersurfaces, we just need to work with the complement. And in the complement, it is easy to describe the Hodge filtration and so on. Okay, maybe in the remaining 20 minutes. So the idea is that I want to move to just Fermat variety, and at the end of the day, to see that over the Hodge theory Fermat variety, it will become just a linear algebra. But for another reason also, I have to restrict to work in affine varieties. So maybe, okay, maybe again I make it wrong. No, not this picture. This. Pn plus 1. Okay, I will look at Pn plus 1 as Pn plus 1 as Cn plus 1 union with Pn. So this will be the Pn at infinity. And well, let me talk about this. So my hypersurfaces is in this Pn plus 1, and one of the first lectures when we were doing topology, I assumed that the X intersect transversally. What is Pn? And this was equivalent to the fact to the fact that let's say maybe I write and then blah blah blah. In a moment I will write. So X. I will assume that Pn is given by x0 equal to 0. So this is and at the end the coordinates here are x1, x1, xn plus 1, because x0 is already put equal to 1. So in some sense, this is the x0 equal to 1 affine chart. Okay, what else? I assume that I use the capital letter f equal to 0, but here I will need a small letter. So x. This part u, or I think I will use the notation also L. So it is given by f equal to 0, and f is just f x0 equal to 1, and then x1 and xn plus 1. Anyway, by some historical reason, and also for from a computational point of view, we have to restrict ourselves to this affine variety. And well, the historical point of view is that a lot of periods or integrals, they are written in affine charts. And also, you will see that the computation becomes much more straightforward in the affine chart. Anyway, so extra intersect Pn transversally, it will be translated into this fact that if we write f homogeneous part, F0 plus F1 plus Fd minus 1 plus Fd, and this Fi homogeneous of degree I. Then I call this one G. It will translate it into this fact that G maybe I write the algebraic version. Dimension Cx1 xn Cx1 x2 xn plus 1 divided by Jacobian of G. Is this also finite dimensional, or in some sense G equal to 0 in this variety here, which I have put it as point, is smooth. Okay, so so what I need to translate the Griffiths theorem to this other part, and so let's try to do this. Okay, maybe I write once again the filter, this Fi Hn plus the Rham Pn plus 1 minus x. So this guy, for the moment I don't need the generators, a basis, but just to the description of the elements of the space. So it was given by, let's say, px omega that I will put there, and then again between this f and this f, don't make any confusion. This is a polynomial. This is Hodge filtration. Fn plus 3. Let's call k, and then k is less than n plus 1 minus I, and then the degree of the denominator. So it is represented by these elements, and then degree of pi must n plus 2 must be k degree kd. Anyway, Fi is generated by these guys, the pole order less than n plus 1 minus I. And so I need the restriction to x0 equal to 1. So let's see what we will get. Maybe so restriction to x0 equal to 1, and then I will use also the notation x for x1, x2, xn plus 1. Here I have used the notation x for x0, x1, and so on. But once I forget the variable x0 by putting it to 1, I can start using x for this one. So this will be, again, I will not use another notation. Here px is homogeneous, and then so omega restricted to where I have written the omega, so maybe I show it here. Omega is this one. So when you restrict it to x0 equal to 0, all of these guys, they have the x0, they will disappear, except the one which doesn't have the x0. And the one which has the x0, there is the x0 here. So x0 putting 1, we will get 1. At the end here, we will get the x1, the x2, blah, 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 the xn plus 1. And here, let's say f restrict to x0, it is a small letter f, fk. And then here now that the degree of p is not necessarily homogeneous. The degree of p, let me say, so And anyway, since we are restricted to x0 equal to 1, so this means the degree of p will be less than kd minus n minus 2. So in this case, p just polynomial, not necessarily homogeneous. And what else? Okay, so anyway, so this we will get this this kind of differential forms, and okay, so I am slowly trying to move to the concept of a Briskon module and Gauss-Manin system. Let me see. Okay, so okay, so maybe well, in general, I don't need really to work with polynomials. So let's just work with monomials. So omega beta. Okay. X beta. X beta. So dx. So from now on, dx will be dx1, dx2, wedge dxn plus 1, fk. In order to put in the notation of my book, a beta, I will define it as, let me see in this context, a beta will be degree x beta plus n plus 2 divided by d. So remember that at the end, x beta is x1 beta 1, xn plus 1. This is just a monomial. And so our condition is, what is our condition? Our condition is that a beta is strictly less than, just a moment. No, not strictly less than, and k equal to n plus 1, then degree p is this one. Just when I'm making okay, just one. I made a confusion. So px the degree of p, that's n plus 10, it must be this one, and it's divided by d. Oh, sorry. No. Okay, now I see what I have. What I have here. Okay, and then actually I made a mistake here. This is n plus 1. Okay, so let me see. I'm trying to write down in the notation that I have done a lot of computation in my book. So I will put this instead of n plus 1 and then n plus 2, n plus 1. So at the end of the day, what I am saying, this a beta is strictly less than degree x beta plus n plus 2 d, and this is the less than or equal to k. So at the end, in our all, a beta is strictly less than k. Anyway, let me a little bit. So these differential forms by Griffiths' theorem, we will need it in order to describe Hodge cycles. Maybe I do something also, another picture also again, before going to Pn. So let's call this variety at infinity y. So x, yeah, so let me see. So y is this projectivation of g equal to 0 is inside this Pn. And at the end of the day, my variety x is this affine variety, the affine variety union with this y. So the idea is that we want to capture the Hodge theory of x by just looking for this affine variety, but maybe in our way we will see. So okay, guys. What I want to say. Okay, maybe for the Gaussian sequence in this case, let me call it the next lecture. But okay, so in general, we will work with differential forms let's say this x with no restriction in x beta, k, and so on. And at the end of the day, let me say something that we will have. Let me see. Okay, okay. Let me. Okay. And at the end, these differential forms, they capture the de Rham cohomology of L. Let me say in this way, Hn plus 1 de Rham C n plus 1 minus L. So I am writing now the residue map okay. These differential form that you see here, at the end they are here. X beta dx fk. And we will need also this residue map. Maybe I have to say, remember that this L here is not compact. And I started from this Gaussian sequence, and which was obtained by Leray-Gaussian isomorphism. And there I was assuming, I have to assume that y is compact. But the definition of the residue map itself is independent of the compactness of y. Anyway, we have this thing in the compact when y is compact, but the residue map itself, it can be defined in arbitrary context. We just need the de Rham theorem, the duality between homology and cohomology, to find the residue map. Anyway, what I want to say that at the end, these differential forms, they are in this space, and I will need this residue of these guys of here, and this one I will define it purely algebra in an algebraic way. That in the future I will tell it. And let me see. You see that the basis that we get from Griffiths' theorem, this A beta is strictly less than chi. There are some restrictions, But for example, maybe I just mention. I think I will put it for the next lecture. Okay. Anyway, so for the moment, I will not prove the Griffiths theorem. I will just try to restrict to the affine part of the hypersurface, and to play with the differential form in the affine part of the hypersurface, and try to compute Hodge cycles and talk about the algebraic cycles and so on. I think for today it is it's done. ¿Alguna pergunta? Bom, se não tem nenhuma pergunta, então mais uma aula eu vou falar sobre a relação entre cohomologia de Rham da parte afim com parte compacta, e depois a ideia é ir para a variedade Fermat. Na variedade Fermat eu vou, primeiro uma aula, vou colocar toda a teoria que precisamos, e depois já deixar claro que já o nosso problema ficou na mesma conjectura de Hodge, ficou só álgebra comutativa, álgebra linear e nada mais. Tá bom, pessoal. Então, se não tem pergunta, ficamos para a próxima segunda. Felipe. Deixa eu ver, Felipe. Você tá... Então, você compartilha comigo agora mesmo? Tá, então, na verdade, ainda bem que você está... É bom você sempre estar gravando, porque não sei, o meu falhou hoje. Eu não estou gravando pelo Google Meet. Tá ok. Tá bom. Tchau, tchau.